Hello, my name is Sahil, and this is my submission for Programming Assessment 2 for the subject of Artificial Intelligence. So, in this assessment, we will be solving 8 puzzle problem using a star algorithm. So, by 8 puzzle problem, I mean is that we have 3 by 3 matrix of numbers 1 to 8 with the null value, and our goal is to find the ascending solution, the clockwise ascending solution of that state. So, we can see the initial configuration and goal state here, and we'll be solving this solution using a star algorithm. So a star algorithm is an informed search algorithm. So by that I mean is that it doesn't just take the cost that has occurred to its consideration, but also the cost that might occur more to find the solution. So what I mean by that is that this is the equation that's basically the core of a star algorithm. So in this L equation, g of x is the cost that has occurred already to go to a till until some certain node x, and h of x is the heuristic or estimated cost to go from the node x to the goal state. So h of x can be calculated by multiple algorithms. We can use Manhattan distance, Euclidean distance, or anything, but for our assessment we'll be using Manhattan's distance. And f of x is the basically addition of the cost that has occurred and the cost that might occur to go to the given goal state, uh, passing via some x node. So that's the basic idea of A star algorithm. So A star algorithm uses a priority queue to get the lowest value of f of x. So that's how it find the most optimal solution, because it try to find the lowest f and x value using a priority queue. Priority queue is sort of like a heap in which the lower value of f and x are stored on top. So when we pop something of the priority queue, we get the lowest fx value. So that's how it works. And for the implementation part, because this is the same algorithm, same problem as the previous assignment one, we are using the same shared function. So we have a display function, finding empty position, checking whether given state is goal state, given move is a valid move. We need to create a copy of matrix because in Python lists are passed by reference, and to convert a given state to a string signature for hashing. For the actual implementation of A star algorithm, we are pre-calculating goal state. So what I mean by that is that we are already pre-calculating that 1 should be at position 0 and 0, 3 should be at position 0/2. So we are pre-calculating the goal state positions. So we are doing this because we just want to make the Manhattan calculation a little bit optimized, so that we don't need to iterate every time to find the Manhattan distance. This is the function for Manhattan distance. So Manhattan distance in this context means that uh, how different the current state is from the goal state. So we are calculating that by checking each and every tile's distance compared to the goal state. So in a given matrix, if if tile 1 exists here, and in ideal state it should have existed here on 0 0, so we calculate that distance and we do the same process for each and every tile and try to find a overall difference between the goal state and current state. So we add that distance, and that is basically our Manhattan distance. So the difference between current state and goal state. For the actual algorithm, we are okay. Yeah, for the actual algorithm, initially find the empty position in the given state, initial state. Initialize our priority queue. Initialize it with the current initial state. So because we have not moved anything, any positions, g cost is 0. H cost is the estimated cost from initial state to the goal state without any intermediate state, and f is g plus h. So we are initializing with this. G cost is a map to store the g cost that have occurred at this point. This is used to compare uh, whether we have found a more optimized G value compared to any previous that we have seen. Parent map is basically parent dictionaries to uh, store the path that we have taken. So it's not used in the actual algorithm, it's just used to print the path that we have taken after the algorithm has executed. So it's not used in the actual algorithm, it's just a utility to visualize the path taken. So while there is some unexplored state in the open list, we pop that list, pop that heap, so we get the lowest f value. Initially it's just the first state. If we check that whether the popped state is a goal state. If it is a goal state, then we have found a solution. If it is not, we try to move in 4 potential directions. If that potential direction is a valid move, we move that move, create a signature. Now because we have taken a move, we increment the cost for this particular problem. I'm assuming that cost of moving each state, each tile is same 1, so we increment the new value in the g cost. So that's a new g cost. If the given state that we are exploring now, that's the x state, if we have never seen that before, or if we have seen that before, it's the new g value is uh, better than the previous g value. That means this path is better than the previous path. Basically we take consider that move, otherwise we just ignore it. So if we consider that move, we store the better g value in our uh, g cost blank dictionary. We use that path, and because we have taken a move, we recalculate our h cost, recalculate our f cost, push that again to the priority queue, and this loop continues until we find our goal solution. If we find our goal state, we return that. If we don't, we just return none. And this is a utility function to print the path, and this is the actual execution. So I use the same test state in given in the assignment, and we can see here that we found a solution at depth 5, number of state explored with 12. Depth here is just basically the cost, g cost, that had we had to take, because we are taking one cost for each tile. It's sort of like a depth for us, and this is the path that we took. So we move up, left, down, right, and we found our solution. So that's how the A star is working. I hope I was able to communicate that efficiently. Thank you for your time.